This is video number 9 for Computer Science 1124, and we're still looking at stuff that we need to know for our Project 3, but I'm going to backtrack just a little bit. Actually, it feels like a lot now. I'm going to call this Binary Data Revisited. It seems like ages ago, doesn't it? There was that big shock, or at least that's how I acted, that it was a big shock that everything that has to be represented in the computer has to be done using nothing but zeros and ones. Zeros and ones galore. Zeros and ones for numbers. I should think we could check that box. We looked at that every which way but loose. The place value system and 2's complement, and the shorthand for binary numbers, also known as base 16 hexadecimal. So yeah, we got that covered. What about for other types of data? For characters. Characters, remember, again, back to an old description. The way I describe a character is that's what you get when you poke the keyboard with your finger one time. So if I were to poke that keyboard up there, then I might hit an A, I might hit a 6, I might hit a question mark. Any of those things has a binary code associated with it. One that's still in common use is called the ASCII system, ASCII, American Standard Code for Information Exchange. You don't have to know that. I'm just impressed with myself right now that I knew that. The ASCII system, just it's really like a table lookup. There's nothing exciting about it at all. We don't do arithmetic operations the way we do with our numbers, but just some examples here. I'm not going to do the whole character set. Capital A is represented as the binary code 0, 1, 0, 0, 0, 0, 0, 1. Is there any way we could have calculated that? Place value chart figured it out? No. That's just the ASCII people associated that particular binary code with A, which is also this binary, but that's also, turns out, 65 in base 10. Now, in spite of there not being any logical basis for why that should be A, there is some logic to this system. For example, capital B is 0, 1, 0, 0, 0, 0, 1, 0 base 2, also known as 66 base 10. Rapidly, we see a pattern developing. If we were to keep going, we would find out that capital Z is, and I don't have this memorized, 0, 1, 0, 1, 1, 0, 1, 0, which turns out to be 90 in base 10. So each one of these different characters, each one of these different alphabetic characters has a binary representation in the computer. So if you type in capital A in your Word document, you're putting a 1, 0, 1, 0, 0, 0, 0, 1 there. I might not have read that off correctly, but you got the idea. Now, there are also codes for digits, not just ABCs. Well, let me get done with the ABCs first. There's lowercase a after that. Now, here's something that might seem counterintuitive. The lowercase a is 0, 1, 1, 0, 0, 0, 0, 1, base 2. And that's 97, base 10. Lowercase b is 0, 1, 1, 0, 0, 0, 1, 0, base 2, which you guessed it, that's 98 in base 10. Now, the only interesting thing for me about that is the lowercase letters are bigger numbers than the uppercase letters. Who cares? I don't know. Some digits, though. How about 0? Well, hang on a second. 0 already has. 0 is just a single bit 0, isn't it? No, it has its own. This is character 0. When I put it in quotes like that, that becomes a picture of a 0, not a real 0 anymore. That's 0, 0, 1, 1. 0, 0, 0, 0, which is equal to 48 in base 10. The character 1, let me get these up here and then see if we can say profound things about them. 0, 0, 1, 1, 0001 equals 49 base 10. Now, I believe on more than one occasion, I've said in the real class, the one where you sit in a desk and I'm up at a real whiteboard, that we got to be careful not to use a picture of a 0 and a picture of a 1 rather than a real 0 and 1. Here's why. This character 0 that I get by hitting the 0 key on the keyboard, that actually is 48. It's not a 0. So if I tried to add character 0 to some number, let's say, remember we did the eval input. Here's what's going on. When you read it in with just input in Python, when you read in a 0, you're reading in 48 from the keyboard. Eval takes that and turns it into a binary 2's complement 0, which will be solid zeros, if there's any logic to the world, for crying out loud, which we can do math with. And when we read in a picture of a 1 in Python, we've got to eval that into the number actual 1, which instead of being this wild and crazy looking pattern, it'd be solid zeros and a 1. That would go on a place value chart. I am struggling here trying to make this interesting. And it's just a bunch of table lookups. These are the character codes that are sent in by the keyboard, and these are the characters they correspond to. And I can't come up with anything more interesting than that. I'll try to finish with a flourish here. All these different characters, all the characters have their own codes. For example, the $sign is 0010, 0100, 36. Base 10, and I'll just finish with the ampersand. Ampersand is 0010, 0110. All these were binary codes, which is what this is all about. How do we represent all these different kinds of data? We already knew how to do numbers. This is how you do characters. This is 38 base 10. 38 base 10. And you can look these up online. There are ASCII tables all over the web. All you got to do is look up ASCII, ASCII, and it shows you all the different keystrokes, all the different binary patterns. And if I've got your curiosity up, oh, what's 37? 37 is a percent sign. And I'll pretend like that's interesting and move on. Okay? Now, I've used up all my whiteboard, so I've got to get rid of all of it. We've looked at numbers. Now we've looked at characters. What does that have to do with us? Well, what it has to do with us is that all kinds of data in the computer that has to be represented in binary. What about, drumroll, colors? How can we represent colors in binary? Well, binary only has two values, 0 and 1. So we could just say if it's a 0, then since that's off, or turned off, or no, or false, then we'll color that black. And if it's 1, then we color it white. Done and done. Well, no, I'm going to have to X that box instead of checking it. That's not very many colors, and I know that my computer can handle more colors than that. The 0 and 1 all by itself was also, if you recall, insufficient for numbers. How did we take care of that? Well, instead of using one bit, we used a bunch of bits. Colors does the same thing. Colors uses more bits. Question, this is not a question, but I'll write it as one. More colors? How do we get that? Answer, more bits. In some cases, a bunch more bits. I'm going to look at a standard system. Standard, because just about everybody uses it, even though it's not the only one. Standard color system for computers. Everything we're talking about in the class is about computers, so I'm not going to glorify that by writing computers on the board. Color system, RGB. Has a little lilt to it, doesn't it? A little tune. RGB stands for red, green, blue. It turns out that in the RGB color system, which is enormous, gobs and gobs of colors, that any different color that you want to represent can be represented by an intensity of red component, an intensity of green mixed in with that, and then an intensity of blue. It's not like the primary colors of paint. I think paint is red, yellow, blue. Does that sound right? If you want to mix green, for example, you got to mix blue with yellow. All those rules are off when you're talking about computers and the colors of light and stuff. So it turns out that we can represent any color we want by varying the intensities of red, green, and blue. What intensities are possible? Well, here I'm going to put the red intensity since that's the first one. The red intensity, it turns out, can be anything between 0 in base 10 to 255 in base 10. Things that make you go, that 255, that rings a little familiar. I think we've seen that before somewhere. Mental note. The green intensity, look what I did. I practiced. I put the markers up here in advance. I even checked to make sure they're still right. I hope they do. Red, green intensity. Red was 0 to 255, but green is 0 to 255. You're probably ahead of me in the notes by now. Blue intensity. Be still. Still not used to the wiggly whiteboard. That's why I misspelled intensity. At least now I have an excuse. That's 0 to 255. Now I'll go backwards since I already got the blue open. 0 to 255. 0 to 255. I think we've kind of seen that range before. Look at this. Or, instead of writing it in base 10, which is the outlier, binary is the natural language of computing. Hexadecimal is shorthand for the natural language of computing. This is double 0 in base 16 to double F in base 16. That's why the intensity is limited to the range 0 to 255, because those are all the positive, non-negative. None of these are negatives. 0 is no blue intensity at all. There's not any blue in your color. FF, that is maxed out. If we change that, that is solid ones. All the little light switches turned on. That's going to have a lot of blue in it. So here's our range. It could be nothing, no blue whatsoever, up to maximum blue. FF. And notice how much more sense it makes in hexadecimal than it did in decimal. I don't even know the name of it anymore. Base 10 is just so far away from us. 0, 0, 16 to FF 16. And 0, 0. This is one of those videos that you might want to fast forward through the second time. FF 16. When they all come together, I'll just leave the caps on. They're not going to dry out before the video's over. If we put all those together, 0, 0 in red, 0, 0, no red for you. The green, 0, 0, no green either. And the blue, 0, 0. It turns out, if I turn down all the colors to nothing, I get back to black. Plain old 0 up there. This is a big fancier 0, but it's still a 0, and that's black. If I specify that hexadecimal color as the color of a circle, the color of a rectangle, ruh-roh, we're starting to bleed in some references to Project 3 here. Then that's going to be black. What if I go the other extreme? FF, max out the red. Turn on all those little red switches. What about max out the green? FF. All the green switches. All the blue switches. FF. Well, that's white. If you turn everything on, maximum intensity, all blended together, it shows up as white on the screen. That's a lot of trouble. Get all the way back to just black and white. Well, here's where all the other colors come from. Let's say, oh, I don't know, red, that's kind of alarming, and I want something calm and less stressful. So I'll turn down that, make that zeros, and do the same with green, make that zeros, and I'll max out the blue. That color will be bright blue. There we go. If the blue component is the only one that's on, these others are zeros, then that color will be bright blue. What about the, well, you can figure out the rest of it. If this one is maxed out, if I use 00FF00 as a hexadecimal specification of a color on my Python program, that's bright green. Bright red would be FF0000. How do you tell Python that these things are supposed to be colors? Well, it turns out there's a convention, standard convention. You make them strings. This is how you would specify black in hexadecimal to Python. Pound sign or hashtag, whatever you want to think of that, inside double quotes, and then you just put your hexadecimal digits. Down here, Python, pound sign, FFF, and these numbers, what do those mean? Let's see. Let's go back to decimal just to get an intuitive lock on what's going on here. That's 0. I know that. 0 and base 10, I can do that without even looking it up. The other one I cannot because it is 16,777,215 base 10. That's a huge value for black. But let's think about this. What that means is in these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 24, in these 24 bits, I can specify a range of almost 17 million different colors. Every one of those bit patterns is going to be a slightly different intensity of red mixed with green mixed with blue. Every single one of them will be a different color on your computer screen. So don't you come up and tell me that you couldn't figure out enough colors for all your rectangles in Project 3 because you've got a choice of almost 17 million different colors to use. Now then, oh, well, one thing I forgot to say. Now we can do colors. I'm going to put the box in check here. Here's what I forgot to say before I erase the board. Think back to the first whiteboard. We looked at numbers, then we looked at letters, and they were both just bit patterns. One of them is bit patterns you slap on a place value chart and away you go. Another one is a bit pattern that you use to do a table lookup and find out, oh, that's a capital Q. What about this business here? All these bit patterns. These are numbers. If I throw that on a place value chart, I get that. But I'm telling Python not to view this as a number, view this as a color specification based on these intensity components. That's key. What's key? What's key is, even though all these different kinds of data are represented in binary, the computer does not automatically say, oh, that must be a color. Or, oh, that must be a character from the keyboard. Or, oh, yeah, I know what that is. That's a 2's complement integer. That's done in software. It's the software's responsibility to tell the computer how to interpret the bit pattern, whether it's a number or a character or a string or a color or any other kind of data, for crying out loud. That's all done in the computer's programs, in the software. In our software, when we do this, when we put something like that in a Python program, especially when we put it in a place where a color belongs, we can assign this to a variable later on and just say, set it to that color and boom, it'll be white. But when we put this in a context where Python knows and is expecting a color there, then there is no ambiguity. It knows that that's going to be white, that's going to be black, and all the red and green and blue and pink and orange and everything else in between is going to, to use that bit pattern to set the intensities for red, green, and blue. I think I've about milked everything I can get out of that. Let me see. Well, I think the rest of it, I was going to try to go in more detail, and this is how you're going to set it up in your Project 3. You know what? I'm going to do an example program. We haven't done a good old example with the trace in a long time. So that'll be the next video. And now, finally, this has been making me nervous. I can close up all my markers before they dry out, for crying out loud, and I'll see you online. Well, that's